So today we are going to understand how to build the binary search tree. Okay. So I'll take an example here. Say 3, 4, 5, 2, 1, and let me take 6. Now when I want to build a binary search tree, okay, this is how I do it. I go to create a node with 3 fields. So the middle one is the info field, and this is the left link, and this is the right link. Okay, in the middle info field I'll go for storing the first integer here, 3, and this is made as the root node. And next I take 4. Okay, I just compare that with 3. So since 4 is greater than 3, so I create a right subtree for this node. Something like this, and 4 is inserted here. Okay, and I make the right link of the root node to hold the address of this node. So something like this, I'll write and show you. Okay, address of this node is stored in the right link of the root node. And similarly, the next the next integer that is scanned is 5. Again 5 is compared with 3, so 5 is greater than 3, and I check the link here. The link earlier it was null and I inserted here. Now the link is not null. That means there a right subtree for this node 3 already exists. So now what I have to do, I have to keep traveling along that right subtree. I travel along this and I reach this node, and again at this node I go for comparing 5. I compare 5 with 4. 5 is greater than 4. Now again I'll check whether I need to travel, so along the right subtree of 4. So and there is no right subtree of 4 because this is null right now. Okay, now that means, so I understood it has to be inserted towards the right side of the node 4. So I create a new node. I'll put 5 here, assign the info field of this node as 5, and in the right link of this node I store address of this. Okay, I again scan 2. 2 is the next integer. I compare 2 with 3. Okay, 2 is lesser than 3. Now I check, I need to traverse along the left subtree of 3, and there is no left subtree present right now because this is null right now. So that I understood. Now 2 should be inserted here as the left child of the root node. I create a node, I insert this, so assign the info field 2, and in the left link of the root node I store address of this node. Okay, next symbol which I am scanning is 1. Okay, 1 is scanned. Okay, I compare 1 with 3, so 1 is less than 3. I travel along the left subtree. So because this is not null now, that means what? I have to travel along the left subtree of 3. I have traveled, and again I compare 1 with 2. So 1 is less than 2. Now I check whether I need to travel. I don't have to travel because this is what? Null, because after this 2 there are no more nodes, no left subtree and no right subtree. Now I understood it has to be inserted towards the left side of the node 2. So I assign the info field as 1, and here I store the address of this node. Next I take the next symbol 6. So 6 is compared with 3. It is bigger. 6 is bigger than 3. Now I understood I have to travel along the right subtree of 3. Now when I look into this field, that means this is not empty. The right subtree already exists. I travel here. Okay, I travel to this, and then again I compare 6 with 4. 6 is greater than 4. I check whether the right subtree for this node exists. Yes, right subtree for this 4 already exists. I travel along that path. Okay, next I compare 6 with 5. So 6 is greater than 5, and I check whether the right subtree for 5 exists. So there is no right subtree for 5. Now I have found, so this is the place where I need to insert 6. So 6 gets inserted here. Okay. Next, if I this is how you got to build the binary, and we got to write a program to do this now. Hope you people understood.
Yes, sir.
Yeah, and here, since this is the leaf node now, and it doesn't have the left child and the right child, now what we do, this is stored with the null, and this is also stored with the null. And here this node has only the left subchild, and there is no right child for this node. So this is null again, and here this is null, here this is null, and here this is null, and both are null here. Okay, so this is how you go to do it. So now how to write the program to do this, or let us write the algorithm for doing this, and then we will go for writing the actual implementation. Okay. I'll go to the next slide here. Now first what I have to do, I have to read the given list of integers. Now when I read the first node, so when I read the first node, okay, I create a node. First thing what you have to do is create a node. Create a node. Now how to create a node? You'll be calling the macro malloc. Malloc macro you'll call. You'll pass some pointer q, and then size of struct list, something like this. So this allocates the memory required for creating the node. Okay, and then what you have to do, you have to assign the info field. Okay, so and I just say again q is equal to, so q will be pointing to that newly created node. What you have to do is q arrow. So let me call info field as info itself. Info. So if you look into the structure, struct tree, let me write it as, instead of list, okay, you'll confuse. Let me take it as tree. Struct tree. Now you have, I'll just show you. So int, one is info field, the other two are pointer to itself. Struct tree star, I'll write below, L link. Okay, and then similarly struct tree star r link. So this is what the structure, this is how the structure looks like. Okay, people understood?
Yes, sir.
Okay, so
Yes,
one
sir.
is the integer info field and two link fields. So this is the integer info field, and this is the self-referential pointer which points to itself. Or okay, struct tree star left link, and this is star right link. Okay. So this is how the structure looks like. What I'm doing now to the newly created node, you have q pointing, and q arrow info is equal to, say, the first node. So from the array I'm reading, okay, the first node which I enter, okay, say it is there available, I've read it to the variable element, so I just say element, q arrow info is equal to ele, element. Next what you have to do, now after doing this, so q arrow when you are initially doing it, so q arrow left link and q arrow right link, you have to make them as null. Q arrow L link is equal to null, and then similarly q arrow r link is equal to null. Okay, and then I make, so this I'll take it as a root node. I want to make this as the root node always. Okay, what I do, so this I want to make it as the root node. I'll just say node. Okay, no, not required. I just say r. So I'll write here node star r. Okay, r is equal to q. What does it mean? I'll write here. So this was the newly created node, or I think I can erase this and show you again. If I discard, I think everything will go. Okay. Okay, I'll erase this. What I'll erase? I'll retain it. This one I'll erase. Here 4 3, and I think we add it as 4. Okay, now what we are doing, see here, node star r I have taken, and then assigning the info field, and who is pointing to this newly created node? Q is pointing, and using Q I'm assigning the info field, and then Q arrow left link is equal to null, Q arrow right link is equal to null. So this is made as null, and this is also made as null. Okay, and then what I'm doing, r is equal to q. Now r is also made to root node, so this is what I'm considering it as a root node. R is equal to q, r is the root node, and it is pointing to this. Next what I'll do, I'll scan my next input symbol or next integer from the list, that is 4. Okay, when I scan 4, okay, so this is when you're creating the list for the first time, tree for the first time, the root node when you are creating. Okay, now what I check, if all these things will be doing if r is equal to null. Okay, next, so all these things, this entire things comes under this of r is equal to null. If r is not null, what does it mean? The root node already exists. So then what you have to do, after scanning the next number, what you have to do? You have to compare that with the info field of the root node. So if r is equal to null, I do these things. If r is not null, then I take this 4 and I'll compare that with the info field of r. Okay, so how to do that? So here, else part I'm writing, else, observe here. So all these statements from here to here, they are inside, they're inside this if. Okay, closing and opening and closing. Assume this entire thing is here. Now in the else part, what I'm writing, else, so if the root node already exists, I go for comparing. Okay, compare the element with the info field of the root node. If r arrow, or otherwise element, if it is less than or equal to r arrow info, okay, if it is lesser, I enter into this. Then I got to check if while So I'll make Q also to point to R. Q is equal to R. Q is also pointing to this, while Q arrow. See, if element is lesser than or equal to R or info, now which tree I need to travel? Left subtree I need to travel. Now, so here Q is equal to R and Q arrow left link L link not equal to null. Correct, right? So while Q arrow left link not equal to null, I should be doing Q is equal to Q arrow, not equal to null. Q is equal to, I'll open the bracket. Q is equal to Q arrow what link? Left link. I have to travel the left link. Okay, I have to travel the left link, and then again I should go for checking the I travel the left link, and then 1 second. I have to travel at the left link, and then it keeps traveling the left link until, okay, every time I travel I have to start comparing also. Sorry, here. And again, if element arrow, if element is, I think I have to put while here itself. Yes.
So free again.
Sir, 11 ಆಮೇಲೆ ಇದ್ದಿದ್ದೆಲ್ಲ ಆಪಿದೆ 11
5 ನಿಮಿಷ ಅಷ್ಟೇ.
ಹಾಂ
11
yes. Okay, so what we will do is this while we will write here itself. Sorry, so let me erase this. Sorry, I made a mistake. So that else is fine, but here, from here I need to erase. So I come to the else part, and then I have to check this element if it is lesser than the info field of the root node. If it is lesser than the info field of the root node, I have to travel along the left subtree. Okay, but I got to do this recursively until I reach the leaf node. Okay. So just a minute. Okay, this is searching. 1 second. Okay, sorry, it's not here. I'll just take it from. I have the function available already. 1 second. Yeah, here is create tree. Okay, yeah, this one. I'll just copy this. Okay, create tree. See, this is recursively called. I'll just show you. I'll take one more slide. Okay, let me show you here. Okay, so all of you can see this, no?
Yes, sir.
Yeah, so same thing what I explained. If p is equal to null, okay, so here we're taking p is equal to null and we create the node, then assign the info field, and initially when the node gets created, we are making the left and the right as null. Okay, here only the name is taken as left and right. Here earlier here while writing I wrote it as left link and right link, so not an issue. Left and right are made to null. So if p is not null, if the root node already exists, then what we do? Else if e equal to p arrow info. Okay, if equal, so what I'm doing, we are eliminating the duplicate entry also. Okay, it should not be same. And then if you want to take the duplicate entries also, if it is equal, then even we go for inserting it towards the left subtree. So if you want to take the duplicate entries also, you got to do e less than or equal to p arrow info. Okay, else if the element which you want to insert, if it is less than the info field of the node to which p is pointing, what you do is this p arrow left is equal to this one. You create tree. Again, this create tree is called recursively. Now which subtree we need to travel now? P arrow left subtree. Okay, so p arrow left subtree need to be traversed. Okay, and what we are passing is the element to be inserted, and the return value from create tree is assigned to p arrow left. Okay, so we come here again, and again we keep doing this until we reach the node where the new node has to be inserted. And similarly, if this is also not true, I go to the else part. Okay, and I check. It comes to else part only if element is greater than p arrow info. Then we traverse what? The right subtree. So this has to be run recursively. Recursively, you should keep traversing either the left subtree or the right subtree until you reach the last node. Once you reach the last node, so there you have to go for inserting your node. Okay, so this is for creating, and inserting there was another function. This is traversal, this is search. Okay, sorry, this itself is also doing the insertion. Okay, because p arrow left is equal to tree, the return value, the newly created node, address is assigned to this p arrow left if it is lesser. If the newly created node, if it is bigger than the info field of the current node, then we store the newly created node address in the right field. Okay, this itself is doing it. So this is how the tree creation works. Okay, so this is what I wanted to show you. So create tree. So this function is called recursively. Here also, when I am writing else, okay, so this is what I was trying to write. So I'll write here else. Okay, if you can take, because else also one more thing you can write, else if this one q arrow, sorry, element, sorry, here else if element is less than or equal to, we'll take q arrow info. Now what we do, q arrow left, okay, or is equal to create tree, and to this we pass q arrow left, and then sorry, comma element to insert. So this is what recursively traversing. Every time I call create tree QRA left, so the left subtree of the node is traveled. Okay, and this is repeated as long as there are few left subnodes. Okay, so else if, and similarly in the else part we go for writing q arrow right is equal to create node, sorry, create tree q arrow right, we traverse the right subtree, q arrow right, comma element. Okay, this is how we create the binary search tree. OP people understood?
Yes, sir.
See this, you cannot apply the condition and keep writing, because you won't be knowing the depth of the tree. So sometimes the tree might be having the tree might be of level 3, or sometimes the tree might be of level 5, or sometimes the level 7 or 8. Since we don't know the depth of the tree, so what we got to do is we got to apply the recursive technique. Okay, when you are traversing either the left subtree or the right subtree, you got to traverse it by using the recursive technique. And you cannot use the while loop also for traversing, because every time you're traversing, it is necessary for you to compare the info field of the current node with the element. So if it is lesser, the element is lesser than the info field of the current node, so then you'll be traversing along the left subtree. If the info field of the current element is bigger than the info field of the current node, so then you got to traverse along the right subtree, and this has to be done recursively. Okay, this is how we do it, and the function is here for the same. Okay, so if p is null, if nothing is there, if the tree is empty, so create the node and then assign the info field, element as the info field. Element here is nothing but he. Assign it to the info field, make both left and right as null. And next, when you scan the other symbol, so p, since it is already pointing to the root node, so this condition is not true. What we do, we come to this and we check whether the element to be inserted is equal to what we are doing in this case is we are eliminating the duplicate entries. Okay, if is equal to info field and I say duplicate entry and discard it. Otherwise I check whether the element to be inserted is lesser than the info field of the root node. If it is lesser, then I go to travel along the left subtree. So p arrow left I give. Okay, I call this function again recursively by passing p arrow left and the element. So the control goes here, and again what we do, this p is, when I say p arrow left, so this p is pointing to the left child of the current node. And next again I compare whether the element is equal to info field, and this process is repeated. And finally, when all the nodes are traversed, what create tree returns to p left is assigns to p arrow left is the address of the newly created node. So the newly created node gets inserted towards the left side of the current node. So if this is also not true, then it goes and traverses the right subtree, and the newly created node gets inserted towards the right side of the current node. Okay, and finally we return p. Okay, p is written finally. Okay, this is how we do it. And similarly, now you understood how to create the binary search tree. So next is how do we travel them recursively using inorder, pre-order and post-order. So this traversal you have already understood, but how to do that in a programmatical manner using the recursive technique. So that is what we discuss now. So that is already here. I'll show you. So we have threaded binary tree also. We'll come to this later. Yeah, here. So traversal. Okay. So Inorder Traversal you have already understood, and this is also done recursively. So if you just observe here, so I'm passing the pointer here. So this pointer will be pointing to the root node. And then Inorder Traversal is something defined like this. If PTR is not null, what we do, what is the order of Inorder Traversal? First it says traverse the left subtree, correct, and then visit the root node and traverse the right subtree. Okay, same thing. So I need to travel the left subtree, no? See, in order, I'm calling this function again recursively. In order, left subtree I need to traverse recursively. P arrow, pointer arrow left child. So till the leaf of the left child is left subtree is reached, so the function will be calling this itself only. The moment it reaches the left subtree, the leaf node of the left subtree, it will go for calling. It comes to the printf statement here, and this when it comes here, the root node is printed. And similarly, once the root node gets printed, so we keep traversing the tree along the right subtree. So by calling Inorder recursively. So Inorder, and what you are passing now is PTR arrow right child. When you want to traverse along the left subtree, PTR arrow left child. Okay, people are following?
Yes, sir.
So this is, so this call will make you to travel the left subtree recursively, LST, and this call will make you recursively traverse the RST. It is easy. So you have to call the same function by passing the address of the left subtree here, and you got to call the same function in order just by passing the address of the right subtree. Okay, and after you traverse the left subtree fully, go for printing the root node, and then root node in the sense the root of the left subtree. Okay, and then go for traversing the right subtree. Okay, so this is how we do it, but you know how to solve the given problem by traversing it along the Inorder, by performing the Inorder traversal. Okay, so now similarly the pre-order. Okay, so pre-order, what was the order? first visit root and then traverse the left subtree and then traverse the right subtree, RST. So same thing is written here. So first I'm printing the root and then calling name of the function. I've taken it as preorder. I recursively call this preorder by passing pointer arrow left child. So PTR arrow left child. And similarly, so again recursively preorder by passing pointer arrow right child. Okay. Understood how the preorder tree traversal is implemented?
Yes, sir.
Okay. So in the other day, the previous day, when I explained you how to traverse the tree in order, pre-order and post-order, I used to write it as what LST and expand LST if the left subchild subtree exists for the current root node, and similarly if the right subtree exists for the current root node, I used to expand the RST. Correct, right? So if in case if I'm traversing using pre-order RST, I used to expand it as what? Root, LST, and then again RST. Okay, same thing. That expansion is nothing but what? This recursive call. Clear, right?
Yes, sir.
Okay. Now similarly for the post order traversal, okay, here see what is the order? First LST and then RST, recursively traverse the right subtree and then print the root node. Okay, so print the root node. So yeah, so name of the function what we have taken here is post order, and what we are passing is traverse the left subtree. Every time this function is called, we have the pointer traveling along the left subtree. Every time this function is called, again post order is called by this argument, it keeps traversing the right subtree and then we print the root node. Okay. Now if I take an arithmetic expression, see in all these examples I have taken an arithmetic expression. So this is the tree of the arithmetic expression. Okay. When I travel this tree using Inorder Traversal, okay, so when I perform the Inorder Traversal of this tree, I get the infix expression. This is what the infix expression what you're seeing. Okay, and similarly when I perform the pre-order traversal of this tree, I get the prefix expression. Similarly when I perform the post-order traversal of this tree, I get the postfix expression. Understood?
Yes, sir.
So if you have an expression, arithmetic expression represented in the form of a binary search tree, then if I want to obtain the infix form of that expression which is represented in the form of a binary tree, binary search tree, then I traverse the tree using what? Inorder traversal. Similarly, if I want to obtain the prefix form of that expression, so then I travel it using the pre-order. If I want the post-order postfix expression, so then I travel it using the what? Post-order traversal. Okay. Okay, so now so this is iterative Inorder traversal. Here what we did, Inorder traversal, we understood how to do it using recursive version. Next, how do we traverse using the iteration method? Okay, so I don't want to traverse using the recursive technique. I just want to iterate and traverse the given tree in Inorder traversal using an iterative version. So this is the program for traversing it along the iterative version. Okay, now what we are doing here, we are making use of this stack to do this here. So top is initialized to -1 and then this is the stack, okay, which is created, and I'm taking an infinite for loop. So there is no initialization. So node, okay, if node is not a null, okay, what I'm doing, I add the node to the top of the stack, okay, and this is repeated. So I add the node to the top of the stack, this is repeated, so until all the nodes I traverse using the left subtree is added, okay. So I take the first node, add it to the top of the stack, and then I traverse along the left subtree. The next node is again added to the stack. Next, what I do, after adding all of them, I keep deleting the node from the top, okay. I pop the top element, assign it to node, and I check here, okay, if not a node, I break, okay, empty stack. Otherwise I go for printing the root node, okay, and we go for traversing it along the right subtree, okay, because in order is what, first you got to travel along the left subtree, and then you got to travel along print the root node, and then you got to travel along the right subtree, okay. So same thing what we are doing by writing an infinite for loop. So this for loop is going to run, and when all the nodes are traversed, we break out of this infinite for loop, okay. When the stack finally becomes empty, we break out of the infinite for loop. Okay, so this is using stacks, how to we traverse using Inorder Traversal technique iteratively without using the recursive technique. Okay, I think all these things will discuss it in this is the tracing operation is also there. So how Inorder Traversal is done using the stack without using the recursive technique. So we'll discuss all these things, and similarly for other things are also there, binary, and so we have this threaded binary trees, okay. So all these things we'll try to discuss it in the next class. Okay. Okay. Okay, any doubts till here?
No, sir.
Okay, so traversing
No, sir.
using iterative technique, using the post order and pre-order, we will discuss it in the tomorrow's class. Okay. $350, $43, $135, $156, absent 10, 16, absent. 39, 116, 34, 134, 135, 136 absent, 137, 138, 140, 141, 142, 143, 144, 145. 146, 147, 148, 149, 150, 151, 152, 153, 154 absent, 155, 156, 57, 158, 159, 160, 162 absent, 163 absent, 164, 165, 66, 167, 168. Nine, 170 absent, 171, 172, 174, 175, 176, 177, 178, 179, 180, 181, 182, 183, 4 absent, 185 absent, 186, 188, 189, 190, 191, 192, 193. Okay, thank you all. We'll meet tomorrow again, and we'll discuss some more concepts on the trees. Okay.